Hi, this is Mr. Anderson, and today I'm going to be talking about radiocarbon dating. Radiocarbon dating is a way that we use carbon and the amount of carbon-14 left in an object to figure out how old that object is. So if we find, for example, a piece of wood that we think was used by ancient humans, we want to figure out how long ago that was. We can use radiocarbon dating to do that. Before we talk about that, we should probably talk about what carbon-14 is. There are three types of carbon that we have on our planet. Good old run-of-the-mill carbon-12 has 6 protons, 6 neutrons, and that's going to be 99% of the carbon that we have in the atmosphere. 1% of the carbon in the atmosphere, however, is going to be carbon-13. That means it has 6 protons and it's going to have 7 neutrons. Both of these are stable. In other words, once they've been constructed, they're not going to change forms. But there's another type, and that's called carbon-14. Now, carbon-14 actually comes from nitrogen. And what happens is that nitrogen is hit with cosmic rays from space, and nitrogen is converted to carbon-14. Carbon-14 has 6 protons, and it's going to have 8 neutrons, and it will decay. In other words, it has a tendency to give off beta particles, and as it does that, it turns back into nitrogen. And so what we can do is measure the amount of carbon-14 in something and tells us how old it is. Now, where does this carbon go? The carbon eventually goes into the macromolecules that make us up. And so when you eat food, you're taking carbon that was once in a plant, but before that, it was in the atmosphere. And so before we get too into that, let me kind of talk about how food gets into you. And so if we look at the atmosphere is made up of a bunch of carbon dioxide. And so this has 2 oxygens, and it's going to have 1 carbon. And most of this carbon up here is going to be run-of-the-mill carbon-12. And so it's just regular carbon. But occasionally we're going to have carbon dioxide that actually has it's carbon-14. So it has those extra neutrons, and so we call this an isotope of carbon, and it has a tendency to decay. And so how does that actually get into our body? Well, the first thing that happens is that plants are going to take in that carbon, and they do that through a process called photosynthesis. And so what photosynthesis is doing is it's a way for plants to take in carbon and actually make something out of it. And so in this case, what they're making is sugar. The sugar is used by the plant to build itself, but it's also used to burn sugar and to do respiration. Now, we don't care about that in plants. What we care about is actually getting that sugar inside our body. And so what I like to eat is something called oatmeal squares for breakfast. It's my cereal of choice right now. And so that carbon that was in the atmosphere, carbon-14, eventually ends up in my oatmeal squares, and eventually ends up in my mouth, and eventually ends up inside my body. And so the amount of carbon-14 that's in the atmosphere is going to be equal to the amount of carbon-14 that's in my body, as long as I keep eating. And so as long as I keep eating, that ratio of carbon-14 to regular carbon-12 is going to be the same over time. But let's say, for example, that I get swept up by a windstorm and I end up dying. It's really sad. Well, at this part, I'm not eating anymore. And so since I'm not eating anymore, I'm not taking in any more carbon-14. In other words, we've cut off that food channel. And so the amount of carbon-14 that I have in my body, I'm stuck with. And so let's say that I'm swept away in a dust storm and I'm covered up by sediment. And years later, a scientist finds a part of me and wants to figure out, well, I wonder how long ago it was that this science teacher met his doom. Well, he or she can figure that out using carbon-14 dating. So how does that actually work? First of all, you'd have to take the bones of Mr. Anderson into the lab, and then we're going to measure the amount of carbon-14 inside me. And we can put me in a chamber like that where we're sensing the amount of beta particles that are given off. But first, let's talk a little bit about the math. At time 0, the amount of carbon-14 that I would have would be 100% of the amount of carbon-14. But that carbon-14 is going to decay over time. And so carbon-14 looks like this, but it's going to break down into nitrogen-14. And as it does that, it's going to give off beta particles. And those beta particles could be measured as hitting the sides of this pretend sensor that I have here. Now we know a little bit about the amount of time it takes. In other words, for a gram of me, and so let's just take a little bit of me. For a gram of me, we would expect that 15 of these beta particles would be released every minute. And so if I were to take a newly diseased or a newly dead body into my theoretical lab here, and if I was getting 15 beta particles per minute, we would know that that is 0 years old. But if we were to look at it 5,730 years later, scientists have found that it would give off 7.5 beta particles per minute. In other words, it would give off half the amount of carbon-14 particles that were in there before. And that would continue to drop off and drop off. And so if we look at this in a graph, this is what's going to happen to the amount of carbon-14 inside my body. 100% of it would be given off at time 0, but every 5,730 years, we're going to give off half that amount. So this drops down to 25%, 12.5, 6.25, 3.125. And so you can imagine that I could create, this is going to be tough to get it good, a best fit line or a trend line of this data. And so what you could do is you could find, let's say we find a bone, and that bone, we could say that it has, I don't know, something like 37% of the amount of carbon-14 that it should normally have. Well, we could just read down here, it's going to tell us how old that is. And so that's how carbon-14 dating works. You could imagine this is kind of a cool math thing. We'll never reach the bottom. It's kind of like walking halfway to the wall and halfway to the wall again. But eventually you get out like 60,000 years, and the amount of carbon-14 that is left is so small that you can't get accurate measurements for that. And so we have to use a different isotope to measure it at that point. Another thing to remember is the amount of carbon-14 is going to drop off, but that's going to be converted to nitrogen-14 as well. And so if we have 25% carbon-14, then we've got 75% nitrogen-14. Now you may be asking yourself, how do we know that this is accurate? In other words, we weren't around there 10,000 years ago, so how would we make sure that your data is actually matching up? Well, what you would need to find objects that are old, but we know exactly how old they are. And so one of the first things that they showed was they took a Egyptian, like a royal barge, that was made of wood, and then they handed it to scientists and said, scientists use radiocarbon dating, figure out how old this is. And so they figured out how old it was. They were able to then go back in the written record and show that those data is going to match up. And so you don't just use one sample, you use multiple samples and different isotopes to get a real accurate kind of a measurement. One caveat to that is this. If you look right here, this was puzzling to me the first time I saw it. And so this is 1945 through 2000, and this blue line represents the natural level of carbon-14 in the atmosphere. But what you see is that we see a peak of that coming right after the 1950s, and it's greater in the northern hemisphere. The northern hemisphere, this would be like in Austria, than it is in the southern hemisphere. It's almost twice the amount in the northern hemisphere, 5 years later than it normally should be. And so the reason why is that humans started doing nuclear weapons testing. And so as we did that, we actually increased the amount of carbon-14 in the atmosphere. And so one thing you should remember is that everything is measured with carbon-14 dating before 1950. And the reason why is that we can't get super accurate measurements within this time because it's kind of screwed it up. So I couldn't, for example, radiocarbon date something from 1970 because it's going to have a different amount, or I'm going to have to somehow compensate for that amount. And so that's radiocarbon dating. It's pretty cool. And it's a neat way to figure out how old the bones are.